Section 3.7 is about some really important angle-side theorems inside of our triangles. The first of which says if two sides of a triangle are congruent, then the angles opposite the sides are congruent. So if I have two sides of a triangle congruent, what type of triangle do I have? Well, it's isosceles, because the definition of an isosceles triangle is a triangle with at least two sides congruent. So sometimes you will hear this theorem referred to as the isosceles triangle theorem. Okay, so if two sides of a triangle are congruent, which is why I'm given AB congruent to BC, that's the hypothesis here, then the angles opposite the sides are congruent. So we are trying to prove this conclusion that the angles opposite AB and BC are congruent. Well, angle A is opposite side BC, and angle C is opposite side AB. So those are the two we're trying to prove. Now, of course, we have to prove a theorem before we use it, which is why we're going through this process. It is a little interesting because our goal here is to actually prove that triangle ABC is congruent to triangle CBA. Now, yes, they are the same triangle, but I did say those letters in a different order, so I can't just say that by the reflexive property. I actually have to go through the steps to prove that that congruent statement is true. So I'm going to start with my given information that AB is congruent to BC. Now we talked very briefly about a property called the symmetric property. And what that says is basically it doesn't matter what side of the congruent symbol you're on. So if I say that AB is congruent to BC, hopefully we all agree that that means BC is congruent to AB. Order doesn't matter around the congruent symbol. So I'm going to write that. BC is congruent to AB. And as I just stated, I'm going to use the reflexive property. I'm sorry, not the reflexive property. I'm going to use the symmetric property as my reasoning. Then, hopefully, you can see that it is true AC is congruent to itself. And here is where I'm going to use the reflexive property, because the reflexive property says anything is congruent to itself. So again, it seems a little weird, but now I'm going to say that triangle ABC is congruent to triangle CBA. What you think about up here makes sense. So A and B were the first two letters here, so B and C better be the second, or the first two letters in the second triangle. And similarly, BC is congruent to AB, so B and C were the last two letters here, so A and B are the last two letters here. So this congruent symbol is true by side, side, side from steps 1, 2, and 3. And the reason I care is if you look at the angles, angle A aligns with angle C, which means that angle A is congruent to angle C because corresponding parts of congruent triangles are congruent. Yay! So, if two sides of a triangle are congruent, then the angles opposite them are congruent. Again, we call this the isosceles triangle sometimes, or if you were going to use it in a proof, we often draw this picture. So put your art skills to use here. If two sides of a triangle are congruent, that implies the angles opposite them are congruent. So you can use this picture on the right-hand side of your proofs going forward, because we have just proven that this is true. And guess what? The converse is true. If two angles of a triangle are congruent, then the sides opposite them are also congruent. We're not going to go through a formal proof again because it's extremely similar to the one we just did, except for you'd switch your given and your proof, so the order would be the opposite. Similarly, because it's the converse, when I draw the picture, I'm going to switch the hypothesis and the conclusion. So if two angles of a triangle are congruent, that implies the sides opposite them are congruent. So this is the converse of our isosceles triangle theorem, and feel free to draw this picture on the right-hand side of future proofs. So, in summary, there are actually two ways to prove a triangle is isosceles. If you can prove that two sides of the triangle are isosceles, then we know, we can prove two sides of the triangle are congruent, then we know the triangle is isosceles. If you can prove two angles of the triangle are congruent, then you also know it's isosceles, because if those angles are congruent, then the sides opposite them are congruent, which gives us our two congruent sides that are in the definition of an isosceles triangle. So be on the lookout for both of those ways in order to prove isosceles triangles. So let's actually do a proof together really quick. I've written this out for you. I want you to go through and see if you can do this proof on your own. Alright, so we always start with marking up our picture. So angle 3 is congruent to angle 4. What does that get you that's going to be helpful? Remember, our final goal is that triangle WTZ, which does not exist. So I'm just kidding. Let's say triangle TRI. Get it? Triangle, try, is isosceles. Okay, so we're trying to prove that this guy is isosceles, and that means we need either two pairs of sides congruent or two pairs of angles congruent. Now, the name of the game for this chapter is congruent triangles, so you can probably look at this picture and guess that we're going to try and get triangle ATN congruent to triangle GIL. In order to do that, we want our given information. So let's go back. Knowing angle 3 is congruent to angle 4, what does that get me? Well, that would get me angle 1 congruent to angle 2 because they are congruent supplements of 3 and 4. I'm given AN is congruent to GL, and I'm given AT is congruent to GI. So hopefully you can see that these two red triangles are congruent by side, angle, side. See the sides, the angle, and the side. And if those are congruent, we know all of their corresponding parts are congruent. So that's going to lead me to angle T and angle I. And if those are congruent, then this entire triangle is isosceles. So that is the game plan. I'm going to write it out and compare it to what you have written out. So starting with my given information, angle 3 is congruent to angle 4. I mentioned the pair of supplements. That gets me angle 1 congruent to angle 2 because of the fact that subs of congruent angles are congruent. Then my other two givens now have the red triangles congruent by side, angle, side, and therefore angle T congruent to angle I by CPCTC. And if two angles of a triangle are congruent, then the triangle is isosceles. The inverse of all these theorems are true. Do you remember what inverse means? It means that you are going to take the negation of both parts. Do you remember what negation means? That's where we're pretty much taking the opposite. You're inserting the word not or taking it out. So, if two sides of a triangle are not congruent, then the angles opposite them are not congruent. And why we care is because we can actually be a little more specific. If two sides of a triangle are not congruent, one of them is going to be larger than the other. That being said, the larger angle is opposite the larger side. And the larger side is opposite the larger angle. So again, meaning the same thing but different directions. Hopefully this actually makes sense. If you picture an obtuse triangle, the side opposite the obtuse angle is going to be your largest side. And the obtuse angle is obviously your largest angle. So the largest side is across from the largest angle. Same thing with a right triangle. If you picture a right triangle, the right angle is the largest angle, and hopefully you remember that the hypotenuse is the largest side. Largest angle across from largest side. And it actually works in all facets. So the shortest side is across from the shortest angle. So if I knew that this was 40 degrees and this was 50 degrees, the side across from the 40 is the smallest side in this triangle because it's across from the smallest angle. And the side across from the 50 is the medium side in this triangle because 50 was the medium angle. And as we already mentioned, the hypotenuse is the largest side, so that's why it's across from the 90-degree largest angle. Looking at this example down here, you tell me which of these sides is the smallest. It should be BC, because side BC is across from the 42-degree angle, which is the smallest angle of the triangle. Smallest side across from the smallest angle. And that about does it.